Yes, Mom. I know it's unseasonably cold out. Why would I need to wear my winter jacket? Snow? In May? Only in Michigan. Okay, yeah, I'll wear my winter jacket. Thanks. I love you too. Bye. My mother is, well, a mother. She's afraid that her little boy is going to freeze to death in this cold. I, on the other hand, am a college student in debt, which means that I'm more concerned about how this cold is affecting the gas bill for my car. You see, when a car starts up from cold start, it's unable to work as efficiently as it does at steady state operation. The engine is unable to burn the fuel quite completely at cold start, and this causes the fuel efficiency to drop. Furthermore, the catalytic converter is unable to filter out the noxious gases until the exhaust gas reaches a certain temperature. And that is why I'm going to work today, to develop the thermal battery technology such that in the future, car mothers can nag their baby cars about staying warm and not polluting so much.
Thermal batteries can store heat in different ways. One way is through the storage of sensible heat, where a material captures thermal energy from its surroundings as it is heated. Water, with its high specific heat capacity, is a very effective material for storing sensible heat. A second method is the storage of latent heat through phase transformation. One such example is the phase transformation of water into ice. Finally, the third method is the storage of thermochemical heat through reversible chemical reactions. These have the highest theoretical energy densities, both by volume and by mass. However, these also require the most study due to kinetic complications. Our goal is to design a thermal battery that can capture waste heat at 200 to 300 degrees Celsius from the exhaust gas and release it at 100 degrees Celsius to the engine during cold start. In this region, we find several relevant chemical reactions that have high energy densities and equilibrium temperatures within the desired temperature range. Take, for example, the reversible reaction between magnesium oxide and magnesium hydroxide. When the magnesium hydroxide is heated between 300 and 350 degrees Celsius, the endothermic decomposition reaction occurs, forming magnesium oxide and water vapor. When we want to release this heat, we recombine the magnesium oxide and water while they are at 100 degrees Celsius. This exothermic synthesis reaction then releases the stored energy in the form of 100 degrees Celsius heat.
Welcome to my computer lab, where I've been conducting my research for the past few months. After spending much time scouring the literature on thermal energy storage, I was able to identify several chemical reactions that were of interest for our particular application, but required more study. And so, I began using a quantum mechanical code called VASP to study these reactions on the atomic level. Even on a supercomputer, these calculations can take some time. This summer has been an amazing experience. I've loved being in a job where I've learned something new every day, and my mind has constantly been stretched. From puzzling over a complicated theory in a paper to trying to understand the results of the VASP code, I've found this job to be enjoyably challenging. And, of course, no great job is without great coworkers. My professor and his graduate students have been very kind to me and have mentored me throughout. Overall, this has been a wonderful experience. Oh, if you'll excuse me, the results from my VASP code should be in now. Thank you very much for your time, and have a wonderful day.